right. 3 different slides, all different shapes, all the same height, all frictionless. I feel like I've seen all these different shapes of slides at different places, maybe in playgrounds or water parks or backyards, things like that. You get slides of all different shapes. Doesn't make a difference in how fast you're going at the bottom. In the first case, in theory, because of course there's no such thing as a frictionless slide in real life. And then in the second case, what about if there is friction, like a real slide? Would it make a difference? Which one would give you the greatest speed at the bottom? Let's think about the case of there being no friction. Perfectly smooth slide. Which of the 3 would you choose to go the fastest by the time you reach the ground? Marshall, what did you say for the first question?
I'm still kind of unsure. I said that they'd all be the same. They all start out with the same. If they're all the same.
Okay, I agree. So Marshall said he's not 100%, but he knows that because they all have the same height, that means you would have the same potential energy in every case. That the potential energy, the energy of height, that MGH that you start off with would be the same regardless of the shape of the slide. Let's take that idea a little bit, Marshall. So when you go down a slide, any one of these 3 slides, what happens to the potential energy that you have? Converted into kinetic energy. Okay. And same height, same potential energy in every case getting turned into kinetic energy. That would suggest the same speed, wouldn't it? In all 3 of those cases. So that's a good answer, and it's the right answer. Okay, it doesn't matter what path you take. If you lose a certain amount of height, you have lost a certain amount of potential energy, and you will gain a certain amount of speed. Okay. And the funny thing is, you don't even need a slide. What if option D was just like dropping straight down to the ground, free falling to the ground? It would be the same speed that either of the 3 slides would give you, because in that case, you would also be losing the same amount of height energy, right? And turning it into kinetic energy. So then the only advantage or disadvantage of using a slide as opposed to free falling is the direction in which you're moving when you reach the ground. So if you look at like slide A, you're going to be going kind of down at an angle at that speed. Whereas in slide C, you're basically going straight towards the ground at that speed, which maybe slide C would be good for a water park or something where you land in a pool, but not so much if you land on like solid ground. A lot of playground slides are actually shaped like slide B, aren't they? Where they kind of flatten out at the end, and that allows the person to get ejected sideways rather than straight into the ground when they reach the bottom. But the speed should all be the same. All right, well done. So what about if there's friction? Does it make a difference? What does friction do to your energy as just in general? How does friction affect energy? What do you think, Lauren?
Well, it's going the opposite way, so it would make you slow down.
So say that first. What was the first thing you said? It's going which way?
In the opposite way of your direction.
Yeah.
So it would make you slow down.
Right, right. So it's a force that's in the opposite way of the direction of your displacement. And does it matter if the slide is curved or straight or whatever? Is friction ever going to be pulling me forward?
No.
No, it's always going to be acting against me. So in all 3 of those slides, friction is going to be acting against me. All 3 of them, it's going to be taking energy away and causing me not to go as fast as I would if there's no friction. Okay, that makes sense. Well, does the shape matter then when it comes to friction? Will there be the same amount of friction on all 3 of those slides or different amounts of friction? What do you think, Amanda? Oh. Okay. So if you didn't hear what she said she feels like C wouldn't have very much friction because, and I think she correctly points out, you're pretty much, for a lot of this slide, you're just kind of dropping straight down. And she felt as though with the slide that was a little flatter that you're going to be kind of pressed harder against this slide. And that's a piece of friction, isn't it, right? The normal force, how hard you're pressed against a surface, and then the texture of the materials. Well, presumably the texture is the same in every case. So if I'm going to be pressed pretty hard against kind of a flat slide, because the normal force is going to be closer to that of my weight, and then if you're kind of falling beside a slide, you're hardly going to be pressed against it at all, that would suggest slide C to not have very much friction compared to slide A. So which one do you think would give you the greater speed then, Amanda? C, one with less friction, will do less work, take away less energy, give you more speed. The only other factor in here that's maybe a little tougher to suss out is distance is also part of work. So, you know, the force and the distance, and it's kind of hard to tell if the distances are different or not. I mean, it's kind of, that would be like how long the slide is. Maybe A is longer than B or C, but it's kind of, I don't know, it's like a little bit of an optical illusion maybe to know even, they're probably about the same length. They look pretty similar maybe. So I'm inclined to agree with her. I think probably C is going to give me the greatest speed. You won't see one like this on the playground because you're going to break your ankles when you hit the ground. You're going to be going fast and straight down. A lot of real slides on playgrounds are shaped like slide B, so that there's a decent amount of friction at the beginning because it basically is pretty flat, and you got to kind of scoot your way along. And you're not going to go before you're ready. And then when you start going, you get a good ride in the middle, and you go pretty fast in the middle. But then that flattening out at the end, it does two things. One thing it does is it sends you out sideways. And the other thing that it does is it produces a lot more friction when it gets flat at the end. And that causes some work to be done, mostly down here at the bottom of the slide. So you have speed in the middle, but then you slow down at the end. And that allows, you know, the kid to kind of recover instead of, I don't know, my son always goes down head first and ends up like, you know, with cuts all over his face and having a good time. That's just sort of his style. So. But I think these flattenings at the ends have saved his life on multiple occasions. I don't know if he'd survive a slide C, though he would try. He would try. So, any questions about the bell work? Makes sense? All right. It was an emotional wedding. Even the cake was in tears. Okay. All right. We're going to do a couple different things today. Not a lot of note taking today. I want to define a couple of terms that you need to be familiar with and do a little bit more example problem solving with our energy conservation problems. You had a slew of them to do for the homework today. And just a reminder to you that those homeworks, the one that's due today has to be submitted online. It's a little different. Usually it's Google Forms. You're uploading pictures for today's homework, so don't forget to upload your 6F pictures. We'll go over any ones that you got stuck on or need a little bit of help on before we start today. And then we're going to spend some time wrapping up our work on our lab that we started last week. The last part of the lab has you reading information off of kinetic energy, potential energy graphs. And the default setting for the software we were using doesn't have those graphs on it. So I have to show you how to get those graphs. We'll kind of walk through that together and make sure you're able to do that. You do not have a homework for next class. So that means that you could consider, like, if for any reason you didn't get the ball toss activity done, that could be your homework for next class. So there won't be another set of problems to do for next time. So just wrapping that up, making sure you're ready. We'll have another homework quiz. Next class will be our last homework quiz for the unit. We're almost at the end of the unit, by the way. We're looking at Thursday for test day. So just a heads up on that. All this stuff's already posted in Canvas, so you can see those dates there too. Any questions before we start? All right, how about homework 6F? Which of those problems can I be of service to you on? Go ahead, Jenna.
Can we do number 2 and 8?
I thought it was Jenna. It was Colin. Number 2 and A. The one about the zip line?
Yes.
Yes, sir. Let's the dot cam here. All right, so we'll set this one up here. This is someone riding down a zip line. You're only given one number in the whole problem. The fact that the height of the zip line is 15 meters, and it seems like you should have to know more than that. But that's all we've got. A zip line is a pretty complex motion. First of all, the line isn't straight. It kind of bows under its own weight. It doesn't even form a parabola. It's kind of a cool mathematical shape called a catenary, but that's just trivia. You didn't need to know that to solve this problem. But basically what you have is you have some kind of a pulley, and then, I don't know, maybe like a seat or something a person can sit on. And they're going to ride down the zip line from one end to the other. All we really know is that the thing is 15 meters high. That's a pretty good zip line, actually. 15 meters is a pretty good drop over the length of this zip line. Now, as the person rides the zip line, what we're asked to figure out is the speed at the bottom, and in particular, the maximum speed, the fastest they could possibly go. So what's implicit in that is we're basically going to assume that there's no friction. Okay, we're going to solve, because if there's friction here, that's going to take energy away and make you go slower. Real zip lines have some friction and the moving parts and the pulley and things like that. But if there's no friction, that'll give me my maximum possible speed. In reality, I'll probably go a little slower than that. So that said, there's really just two forces acting on a riding zip liner. There is a normal force between the pulley and the cable, and then there's the force of gravity, which is pulling the person downward. So from an energy perspective, we have a normal force, which we can effectively ignore, because the normal force is always, regardless of the shape of the zip line, the normal force is going to make a 90-degree angle with the path of motion. So it's not going to pull the person forward. It's not going to pull them backward. It's simply not going to do any work at all. If I bring gravity into the system, so remember we're kind of modeling this by drawing this in the form of a picture. So we've got the person and the earth together as my system. Then that means the environment, which is like the line, the air, things like that, no work is being done. There's no energy being added or subtracted since the normal force isn't doing any work. There's no friction. So we have just a simple exchange that's happening in the system of potential energy changing into kinetic energy. So in this problem, if you write our energy conservation equation, I told you it was the same formula for every one of these. This one here, I would probably set this problem up. My kind of way, I think, of making these easy is to pick the lowest spot in the problem and call that the height of 0. So that means this person's going to start off with some potential energy at the beginning and no kinetic energy. No work is going to be done since there's no friction and the normal force is perpendicular. And then at the bottom, they're not going to have any height, but they're going to have some kinetic energy. So I'm just setting the potential energy equal to the kinetic energy. The mass of the person doesn't matter. That's interesting. It doesn't matter whether it's a big or a small person. They're going to be going the same speed at the bottom. And it's the same exact speed they would have if they just straight fell 15 meters. It's kind of like our bell work today. Except the zip line is going to allow them to be moving sideways at that speed. And a lot of real zip lines, what they'll do is they'll drop you about 15 meters, and then the line will kind of curve upward like this. So it will give you some room to sort of slow down on the other side, so you don't just like slam into a tree at the bottom or something really fast. Is that helpful, Colin?
Yes, thank you.
You got it. Any others we can set up together? Amanda. Yeah, the last part of number 8. So 8 was a two-parter with the roller coaster. Yeah, and part C. Yeah, that's a good one to look at together. So you got a roller coaster car. And the track does something like this. And the roller coaster car starts off up here. And the part you didn't ask about, part B, where it's just how fast it's going at the bottom here. And that's exactly the same kind of thing as this, right? Where we're just going to change the potential energy into the kinetic when it gets to the bottom of the hill. What we can do for part C, because part C refers to when the roller coaster car is here. Let's see. There's a couple of ways we could deal with this. Let's do it this way, though. Let's just pick the low spot to be the height of 0. And so what that means from an energy perspective is that my roller coaster car is going to begin with some gravitational energy and no kinetic energy. And then by the time it gets to this spot on the track right here, it's going to have an energy that's a combination of two different forms. It's going to have some potential energy here in spot C because it's not at a height of 0, and it's going to have some kinetic energy here in spot C because it's, it's a split between the two. So just like the guy riding the zip line, assuming no friction acting with the track, the normal force, again, the normal force is always going to be 90 degrees to the motion. So it's not going to do any work. This, again, is a situation where no work is done. I can set the beginning energy equal to the ending, and the masses cancel out. We can find the speed. That's one way to do it. Another way to do this, maybe this is easier if you like. You could say, hey, where the height of 0 is up to me. I just got to pick a spot. So I could just say that the hill C is the height of 0. And if I did that, then that would change the calculation a little bit. It would change it so that it didn't have any potential energy. I'm just changing all my potential into kinetic. But then you would have to reevaluate what height 1 is. It wouldn't be 25 meters anymore. It would be the height of this hill minus the height. It would be how much higher this is than that hill. It would be, you have to be 10 meters. And you'll get the same answer. So maybe that's an easier way to do it. Was there another one we wanted to go over? I thought I saw another hand. Or 2 other problems, right? Anybody at home have one they want to look at? Okay. Alrighty. So then let's do a little bit of vocab here. It's only new stuff for today in our notes. No new big ideas, just some names for them, really. When we think about energy, so we'll call the topic for today different types of forces. And of course, there's lots of different categories for forces. We could talk about field forces, contact forces, talk about the fundamental forces or forces, whatever. There are different ways we could designate forces, but I'm talking about from a work and energy perspective. When we talk about work and energy, they're really just 2 different types of forces you need to be aware of. And we have a category of conservative forces and a category of non-conservative forces. And other than voting Democrat or Republican, there are other differences between these 2 forces here. In all seriousness, with a difference, what does it mean for something to be conservative? Just in general, what does it mean? What does the word conservative mean? What are we saying, Jack, when we say something is conserved? Okay. Yeah, what do you mean by that? Oh, okay. Yeah, being like reserved, kind of like maybe a little shy or like not outgoing, that sort of thing. Yeah. Well, think about like our unit. We're studying energy, and we said energy is something that's conserved. Like, what do we mean by that when we say energy is conserved? Yeah, that's a good way of putting it. It's stored up. In other words, if I have some energy, I can put it someplace or I can move it from one spot to another, but what can't I do with it? Yeah, I guess it depends on what we mean by that. So I'm fishing for a certain answer, so I won't keep picking on you. What am I fishing for, Amanda? Yeah, I can't create or destroy it. So that's why the idea of storing it makes a lot of sense. You can store it, you can move it, you can even use it, but if you use it, it goes someplace and it ends up somewhere else, right? I can't just make it go away, or I can't just make it appear out of nothing. Okay. So that's what the word conservative means, and we use it in politics. We say somebody's a conservative because what they're ostensibly trying to do, or the literal definition of that means, is they're trying to keep things the way they are. They're trying to maintain some sense of status quo rather than change. And so to be conservative is to keep things the way they are, and energy, the universe, is actually a very conservative place.
We've never observed the universe to allow energy to disappear and stop existing. There's always the same amount. Right? So we're not talking about energy here, though. We're talking about forces that are conservative. So what do we mean by that? I'm going to kind of list some of the properties of these forces. A force that's conservative is able to store up energy. So that's why I liked your answer, Jack, of storing being associated with conservative, because to conserve means to save something. So a force that's able to store up energy, we call, oops, I can't write the word. We call this, of course, potential energy. So any force that can store up energy, and as opposed to no force can destroy energy. So what we mean by that is that the energy is not lost. And I'll put the word lost in quotes because you really can't destroy energy. But what we mean by that when we say energy is lost is we say turned to sound, vibrations, and heat, etc. That there's certain types of energy that it turns out you can't ever get back. Like if I eat some food and like store up some energy in my body by eating that food, and then I use that energy to like clap my hands, like where did that energy go? Well, it made some noise, and that noise kind of spread out through the room, and there's no way that I could ever capture that noise back again and like use it to do something. That is gone. It dissipates. It sort of dissipates throughout the universe, and we call that lost energy. Not destroyed, just spread out, and it's not in a useful form anymore. So the forces, there are a few different forces that meet this category. The one that we've looked at so far, of course, is gravity. Gravity is a conservative force. You can store up energy and height. And so we call that GPE, the potential energy stored up in gravity. But there are others as well. We'll look at this a little bit later in our course. One of the last things we'll look at before our course ends, the ideal spring. An ideal spring is kind of a frictionless, noiseless spring. And there's a type of energy we talk about in stretchy or springy objects called elastic potential energy. When you stretch a spring out, you do some work to stretch that spring out, and then you put some energy in it, and you can get that energy back by letting go of the spring. Okay. And then electric charges, which is basically the whole science of chemistry, is the study of how atoms stick to each other electrically, covalently, ionically, whatnot. And electric potential energy is energy stored up between charges that attract or repel each other, kind of like how gravity causes masses to attract or repel each other. And it's kind of fun because we use EPE for both of them, which is a little bit confusing, but you have to know based on context whether we're talking about elastic or electric. I don't know if I've ever seen a problem that had charged springs in it. That would be kind of confusing, but I guess you could potentially have that kind of problem. Ha ha ha. When you have a force like one of these things, a spring or gravity or an electric charge, our strategy is to always include in the system. So we're not going to take these conservative things. We're not going to let them stay in the environment. We're not going to allow them to do work. Instead, there's a type of energy associated with them so we can bring them into the system. And then finally, the work done, or if we have them in the system, as I just said, the energy stored for all the conservative forces is not path dependent. And we saw this in our bell work today, that the three different paths of the slides didn't matter when it came to how fast we were going at the bottom, because the type of force that was making me go to the bottom was gravity, and gravity was a conservative force, and the potential energy was just based on my height, not the path I took to change that height. So we just kind of draw a picture to sum this all up. This is what a conservative force is. So suppose that I had some kind of a mass like a bowling ball, and I was going to have this bowling ball, I don't know, let's say the height right here is 0. So in this position, the bowling ball Earth system has no potential energy. But if I move the bowling ball to a different spot, like over here, then it will have some potential energy when it's at height h relative to this spot here. And if I move the bowling ball, the simplest way to do this would be just to move the bowling ball in a straight line from the one spot to the other, and I would gain some potential energy. But we talked about this before. I could actually take any path I like. I could take a kind of a curved path like this. I take some kind of a screwy path that makes a little loop-to-loop and goes up higher and then comes back down, something like this. And regardless of which one of these three paths I take, it doesn't matter. I gain the same amount of potential energy in every case. Okay. So in this picture, my gain in gravitational potential energy is just mgh, because I started with 0 and I ended with the height h. And the work done by gravity, which is just two different ways of saying the same thing, that if gravity is in the system, I talk about potential energy. If I leave it outside the system, I can talk about the work that it does. The work done by gravity is going to be negative mgh. So in other words, when you move something up, you gain potential energy, but you're going against the conservative force. So the force is doing negative work. It's taking energy away from you as you do that. If it's outside the system, it's taking energy away. If it's inside the system, it's storing it up. Kind of two different ways of saying the same thing. And that's true for all three of the paths. The paths don't matter. So there's one reason why work and energy is such a nice way to solve problems. You don't have to worry about how you get there. It's just a matter of the height you have. All right. So not every force is this way, though. Only forces that store up energy and then turn it all back to you without creating any sound, vibration, or heat. So it turns out most forces don't do that. And our second category are non-conservative forces. Basically the opposite. Everything that's true about conservative forces is not true for non-conservative forces. Okay. So a non-conservative force can't store up energy and return it all back, because the non-conservative force is going to waste some of it. It's going to create some heat, sound, etc. And the work done by a non-conservative force is path dependent. It matters what path you take to go from one spot to the other. And we find that a longer path equals more work. Farther you move something as it goes, experiences a non-conservative force, the more energy would be added or subtracted by that non-conservative force. And instead of bringing it into the system, our strategy is going to be to leave in the environment. So the forces, the only thing I'm going to bring into my system is the earth and springs or maybe electric charge, but all other forces are going to have to stay in the environment because they can't store the energy up and give it back to me. They're just going to create heat. It's hard to measure heat in a system, so we leave that outside of the situation. So I'll draw a picture to go with this one, just like we did before. I'm going to, oh goodness, I'm going to try to draw a three-dimensional picture here. So draw kind of like a, we'll even do some force perspective here. Suppose we have a region of ground, a rectangle that looks something like this, kind of stretching away in the distance. And then I've got, draw some kind of box here. Sitting here on the ground. And let's say that I move the box from one spot to the other. I push it across this ground. So let's say I push it to some distance farther away. So I'm going to draw the box smaller over here. So it looks like it's farther away, but it's the same box. Okay. So I'm going to move the box from this position to that position. Now, just like lifting a bowling ball up, you can take lots of different paths to, go from one spot to the other. I'll just draw two of them here. Let's suppose that I could just move it in a pure straight line from the one spot to the other. Shortest distance from the beginning to the end. Let's consider that versus like a different path. Let's say I took like a longer path, like this one right here, kind of winded it around and came to the spot over here. Now, as I move this object along the ground, friction is going to act against me. So we think about the different forces that fit this category. The main one that we're going to be dealing with is friction. Friction produces lots of heat. It produces lots of sound. It takes energy away from objects, but other forces like drag, air resistance, okay, these forces are non-conservative forces that dissipate energy from the system. So if we think about the friction force, it's kind of like, I think Lauren was saying earlier, friction always opposes your motion. So regardless of the path, like if you move along this path and you're like right here, here's friction resisting your motion, acting the other way, and you get a little farther and friction's still resisting your motion and acting the other way, and you get a little farther and friction still resists your motion. Oops, not sure why I changed the letter. F again. So everywhere along the path, friction is resisting your motion. And so if we wanted to figure out how much energy was lost in this case, I'd say, well, how much work did friction do? So I'd apply my work equation to friction. I do FD cosine of the angle between them. And the angle between the two, so my displacement is one way and friction is the other way. So since they're opposite of each other, it's going to always be the cosine of 180. Friction always acts to oppose my motion. So the cosine of 180 is -1. I find the work done by friction is going to be negative FD. So the bigger the friction force is, the more energy you lose, but also the farther you move, the greater the distance is, the more energy you lose. And that's even true. You can see that in these two wiggly paths that we'll lose a certain amount of energy taking this path, but we lose even more energy taking this path because along this path as well, friction is going to act against me. And its direction might be various directions, but it's always going to be opposite of the way that I'm going. Draw some different friction forces here. So friction is always opposing my motion. So even on a complicated curved path, friction is still going to be negative FD, and D is going to be the length of this dotted line. So the longer the line is, the more energy is lost to my non-conservative force. So we'll just introduce a very slight, this is the end of our notes here, just a slight difference in notation now. What we can do is we can now rewrite energy conservation, where we have E1, our total energy in our system, our total mechanical energy, plus work equals E2. And our strategy is that these energies contain all of the sources of potential and kinetic energy. So then that means that the W is not just the net work, but we'll call it NC, the work done by the non-conservative forces. Forces that don't store up energy. So these oftentimes are forces that take energy from the system, but they could also be forces that give energy to the system. If you come along and kick a soccer ball with your foot, you're going to give energy to that system. You're acting as a non-conservative force, your applied force on the system. Okay. Nothing too new, just some new terminology and the idea that the path matters when you lose energy, but with the conservative forces and potential energy, the path doesn't. Any questions? All right, well, I'd like to try two more examples here together. I want to do one kind of for you, and then I'm going to have you try one on your own here. These are from the same sheet you were doing your homework from. And make sure I do the right one here. I don't want to do one that I already assigned for homework. That would be kind of silly. I did not assign number 5 for homework. I'm like 99.7% sure I didn't assign this one for homework. That sound right? Okay, thanks. I was originally going to make it be a sledding problem, but, you know, hey, it's gotten warmer outside. It's time to start thinking about the slip and slide. My sweet daughter, she's got like 2% body fat, and like a breeze blows across the room and starts shivering uncontrollably. But as soon as like April hits, she's like, "Dad, can we plug the sprinkler in? Can we plug the sprinkler in?" Like, no, you're gonna die, honey. Gotta wait till July. But this is her. She's just dying to get out there on the slip and slide in our backyard. So we'll make this be Kirsten. instead of a random boy. 25 kilogram Kirsten slides down the slip and slide. She stops after traveling a distance of 12 meters. The frictional force on her was 50 newtons. What was her initial velocity at the top of the slide? So we're looking at this from an energy perspective. There's some friction present because we're told the force of friction is present. So we're thinking, hey, we've got a non-conservative force acting on her as she slides down the slide. And if I went let's tweak this picture a little bit. We'll add the other forces present. There's a normal force, of course, from the ground. There's gravity pulling downward, and there's going to be some friction resisting her as she slides down. So in this situation, Kirsten is going to be part of the system because I'm looking at trying to predict her velocity, but I'm going to bring all the conservative things into the system. I'm going to bring the Earth and its gravitational pull into the system. But the other things like the slide are going to be in the environment. So the slide, of course, that would be the normal force, but it would also be friction. Those are the two forces that the slide exerts on her. The normal force isn't going to do any work at all because it's going to be perpendicular to her motion. But friction is going to do some work. And what we expect to see is friction doing some negative work, friction to steal some energy away, keeping her from going as fast as she should. If it was a frictionless slide. And we're going to see some energy conversion happening here. We're going to see in this system, my daughter starts off with some height, some gravitational potential energy. But we're asked about her velocity at the top of the hill. So she also starts off with some kinetic energy. And when you ride a slip and slide, you don't just sit down on the slide and start sliding. You run and jump on the thing. So you start off with some speed and you start off with some height. And then what's going to happen to that energy? You're going to lose all the height and you're going to end up with just kinetic energy. So you should be going faster by the time you get down to the bottom. If there's no friction, all of your speed and height turn into kinetic energy, but with friction, some of it's going to get bled off. It's going to be lost from the system. So let's see. Let's kind of fill out my picture here. There's a few other numbers given to me in the problem. The distance is 12 meters. That's like how far she slides. Force of friction is 50 newtons. And the height of the hill is 2 meters. So what we can do is we can call the height down here at the bottom 0, and the height where she starts 2 meters. Pretty much hits everything. I guess we're giving her mass as well. I can write that down here. Bring everything into my picture, 25 kilograms. Now my picture is complete. It shows everything that the problem is telling me. So every one of these problems, we're just looking at energy conservation. Hey, the system starts off with some energy, the Kirsten Earth system. Non-conservative forces, if they're available, do work. Yep, friction's here. It's going to be taking some energy away. I don't have to worry about gravity doing work because it's part of the system. I don't have to worry about the normal force doing work because it's 90 degrees to the motion. So this non-conservative, that's just friction. She'll end up with some energy at the end. So initial energy she starts with is height energy. Friction's going to do some work. And by the time, oops, I'm missing something here. Wait a second. She also has speed. I said that, but I forgot to write it down. She has two forms of energy initially. She has height and speed. And in the end, she just has speed and no height. So I should be able to take this picture and start plugging some numbers in here and figuring out, in this case, the initial speed, how fast she's going when she jumps on the slide to begin with. I can't cancel the mass out, though. I've got mass in these three terms, but there's no mass in this friction term right here. So can't make that one go away. So let's plug the numbers in. We got 1/2 times 25 kilograms times v squared. We don't know what her starting speed is. It's 25 kilograms, 9.8 times 2 meters. So this is the energy she starts with. Some kinetic and some potential. Then we have friction doing some work. Well, I don't know how much work friction does, but I do know the force and I know the distance, so I can figure that out. Remember we talked about the work being done by friction? This negative work done by friction is the force times the distance, because the force and distance are always in opposite directions from each other. Even if the hill is curved, when you're moving one way, friction's the other way. It's going to be negative work, and it's going to be 50 newtons of friction times 12 meters of distance. That's how much energy. So she starts off with some energy. Some of it's going to get lost due to friction. And she's going to end up 1/2 times 25 kilograms times, what's her final speed? 0. Yeah, I don't have that in my picture, but it does say that she stops after traveling 12 meters, right there in the initial statement. So, well, that makes things simple. That means she ends up with no energy at all. Okay. So the unknown variable here is v, her speed. We can solve for that at the top of the slide. Should give myself a little more space, but here, if I solve this equation for v, my unknown, I should get 3 meters per second, which sounds reasonable for a slip and slide. That's about 6 miles per hour. See my daughter trotting up to the slide and jumping on. About 6 miles per hour. It's a little jogging pace, I guess. Okay. Any questions? I want you guys to try a problem like this. Very similar problem. Let's see if you guys can reason through it yourself from beginning to end. So here we go. I didn't assign this one for the homework already. Number 9. I'll leave this up here on the screen. I'd like you guys to draw a picture. Give this one a whirl. What's that? Was 3 meters per second for the last one. A little bit more. So start by turning it into a picture, something you can visualize. The numbers in the picture. I guess this question could be misinterpreted. When I say a moving truck, I don't mean that the truck's actually in the process of moving during this problem. I mean, it's the kind of truck that takes you and your possessions to a new house. But basically, it's a crate sliding down a ramp. The ramp sitting still. Okay, so there's my picture. Just turning it all into all the numbers in the problem, bring it into something I can visualize. Distances, the speeds. I have to pick where my height of 0 is going to be. Very similar to the slip and slide problem. Same thing going on with energy. It starts off with some speed and some height. Friction does some work, takes some energy away. Check your answer. If you do the math right, you should get friction doing negative 781 joules of work. Let's see the setup here. We know how much energy the box starts with. It's a combination of its potential and kinetic. We know how much it ends with. It's all kinetic. It's not the same amount. It loses 781 of those joules that it started with by the time it gets to the bottom. And then part B asked me to solve for the force. So if you know the work done by a force, it shouldn't be hard to solve for the size of the force. You know, the work done by friction is negative FD. It's cosine of 180 is where the negative sign comes in. You can plug the numbers into that because we know the distance. It's going to be 781 divided by 5. 6 newtons. All right, any questions? You okay with this one? Encourage you to look these over. I mean, you're going to be, when you do the next homework quiz, it'll be questions a lot like these, energy conservation questions like the ones we've been practicing here. So make sure they make sense to you. All right, well, we're cooking right along. We're doing pretty good. We may finish early today. The only other thing we have left to accomplish is finishing our ball toss lab up. And so I'm going to transition to that. Let's just take a minute or two.
you guys can go ahead and open up graphical analysis on your Chrome, the Chrome extension, and open that file up again. And once everyone's kind of there, I'm going to take a few minutes to show you how to create those energy graphs that you need to answer the last set of questions on the lab analysis. We'll just do that part together. You'll need to be able to follow along with me, so I'll kind of let people get there. Anybody need any more time? Need a minute? If you don't say something, I'll assume we're ready to go. I'm going to go ahead and open the file up. The data that I shared with you guys. Do I still have it? Oh, good. There it is. Okay, so this is the data I originally shared with you. And the first set of questions were all about just looking at that tossed basketball, its position as a function of time, its velocity as a function of time. Just a reminder to you, when we look at this situation, the velocity graph is really what's helping me to see when the throw happens. That I'm really kind of looking at this region right here as the time when the ball was in my hands, and then it's gradually given some speed, and it's only when my hand lets go of it that it starts to slow down. And this nice, steady, constant slope. The slope should be about 9.81, by the way. This slope of my velocity graph is the acceleration of the object. And then this last region right here is basically the catch of the ball, where I take its velocity away, and it looks like I caught the ball, and then maybe when I caught it, I kind of rebounded. Maybe I lifted it a little bit, gave it a little bit of upward velocity, and then stopped it. So it's kind of a little bit of a wiggly catch that I gave it. But the free fall part of the motion, and the ball's only under the influence of gravity, is kind of happening during this region right here and the corresponding region on this graph. Okay. All right. All that to say, we now need I need to put an energy graph here as well. Look at the kinetic energy and the potential energy. So let's set this up together. In the upper right-hand corner, you have this button right here. It looks like a bunch of little windows. We're going to click on that, and we're going to change it to 3 graphs. So we got a place to put an energy graph as well. And I think the default, it looks like it threw an acceleration graph down there for me, not a energy graph. So I'm going to have to change this acceleration graph into an energy graph. That's pretty easy to do. We can do that together. But we need to be here first. So if I go too fast, or if you get behind, just say something, speak up. I can't actually see the Google Meet right now, so you'll just have to turn on your microphone and say, Feldman, slow down. Okay, if you go over to the left side where it says acceleration, basically if you were following the instructions for the lab, it said basically click here and then turn energy on. Well, I can't. There's no option for turning energy on. I just have this last graph which has acceleration. So what I'm going to do instead is I'm going to take the 3 little dots to the right of acceleration. I'm going to click on them, and I'm going to have this logger or graphical analysis find the kinetic energy for me. So I'm going to add a calculated column. So I'm going to click on this, add a calculated column, and it's going to ask me to create this. So I'm going to give it a name. I'm going to call it kinetic energy, or you could call it KE if you like. Energy units are joules. 3 decimal places is fine. So when I click insert expression, basically what I want it to do is I want it to do 1/2 mv squared, which is the equation for kinetic energy. 1/2 mv squared. So I'm going to click insert expression.
And I get a bunch of options of different types of expressions that I can insert. And the one that I want to pick right here, I want to do 1/2 mv squared, so a number times something else squared. So this one in this upper left-hand corner is going to work for me here. It's a times x to a power. So go ahead and click on that one, a times x to a power. It's in the upper left-hand corner. And I've got a place here where I can do 1/2 mv squared. I just have to type the numbers in. So once I have that selected, parameter b, which is the power, I'm going to change its default as a 1. I'm going to change it to a 2 because I want to do velocity squared. This drop-down menu right here says, hey, what do you want to square? I don't want to square acceleration. I want to square velocity. I want it 1/2 mv squared. So the number that gets multiplied by v squared should be half of the mass, 1/2 times the mass. Well, I gave you the mass of the basketball last time. It was 0.59917 kilograms. Well, I want to do half of that, though. So I'm going to divide that by 2. I'll go ahead and type that in here. Half of the mass of the basketball is 0.299585 kilograms. 0.299585. 0.299585. Everybody there, click apply. Okay, great. Well, it didn't change anything, but I go over here to my acceleration graph, but now I have the option to change it into a graph of kinetic energy instead of acceleration. So I'm going to turn off acceleration. I'm going to turn on kinetic energy. Now I have a plot of the kinetic energy of the object. You're going to need to make your own so that you can scroll over it and read the values off the different parts, though. So anybody need me to repeat anything or help you with anything? Because before I do the next one, the potential energy, go ahead. You have to speak out.
Yeah. So my computer's been glitching. I missed like how you get the free graphs available.
Oh, the very first part.
Yeah.
Yeah, it's up here at the upper right-hand corner. These little windows says view options. When you click on that, it lets you change it from 2 graphs to 3 graphs.
All right. Awesome. Thank you.
Okay. Anybody else have any snags along the way? Oh, this is kind of funny. I noticed, I'm not sure why it did this, but I noticed it took my second graph, which used to be velocity, and changed it into kinetic energy. What the heck, man? Let's change it back to velocity. That's kind of weird. It's making that one be that one. That one's okay. You might have to play around with turning the different velocities on until it turns the middle one on. I don't know why it's doing that. There we go. Acted a little funny. I had to change the middle one back to velocity. All right, ready for potential energy? I'm going to click on this bottom graph, the one where I placed a kinetic energy graph, and I'll just kind of do the same thing I did before, where I click the 3 dots to the right of, it doesn't really matter which one, I'll click to the right of acceleration here. I'm going to create another calculated column, this time one for potential energy. And I'm just going to call it GPE. We'll be short, gravitational potential energy in joules. And I'll do the same thing, insert expression. I want a gravitational potential energy is MGH. MGH. So basically the mass times gravity times the acceleration of gravity times the height. So this can be a simpler one. It's just going to be a couple of numbers multiplied together. So we'll just do, actually, which one do I want to do? I want to do, let's do this one right here, this linear one, AX plus B. AX plus B. So it's going to be some number times another number plus another number. Well, I don't want to add anything to this, so it'll be plus 0. I want to do mg times h. So instead of acceleration, it's my position. My position is the height. And then this number right here needs to be the mass of the basketball times 9.8. So I can calculate that in my calculator. I'll take that mass that I gave you, 0.599 kilograms. I'm going to multiply that by 9.8. And that's 5.87. So 5.87 times the position should give me my potential energy. And I'll click apply. Goodness, for some reason it changed my top one to gravitational potential energy. That's fun. They're monkeying around with me. I'll have to get that top graph back. But now on this bottom graph, I can put potential energy and kinetic energy on the same graph. So my potential energy graph is going to look a lot like just the toss graph because it's basically the height of the object multiplied by mg. And then my kinetic energy. I have to change this first one back to position. It's actually kind of funny. There we go. I had to do that on data set 3. There's one more that I have to add. I have to do a graph for the total energy. Is there anybody, did I lose anybody with the first two, with the kinetic or potential, or with kind of getting the top two graphs the way that they should be? Let me know. I won't leave anybody behind. Okay. The last one should be pretty quick. I want to put the total energy down here on the bottom as well. So you know the drill now. I'll click on the bottom here, click on the 3 dots next to any of these here. I'm going to create a calculated column. Going to be the total, we'll call it the total mechanical energy. And I want that basically to be both my kinetic and potential energies added together. So when I click insert expression, I'm going to pick, I want to add 2 different columns together. This, yeah, AX plus BY, that'll work. And we'll just leave A and B as 1. And we'll add the GPE to the kinetic energy. So it'll be 1 times gravitational plus 1 times kinetic. There you go. And then I'll have to turn that one on. Yay. So we should see something like this down here in my bottom graph. The total energy is the one in gold. And what I notice about the total energy, which is the sum of both the blue and the red curve, is that during the throw, during the free fall part of the motion, it's basically a pretty steady value. That I may be gaining one type, but as I gain one type, I lose the other type. And as that type gains, the other one gets lost, but the sum of them is staying the same thing. That supports that idea of energy conservation, that the amount staying the same. Okay. Gave you something different. For the total mechanical energy. I had 1 times the GPE plus 1 times the kinetic energy. Yeah, so the expression that we wanted to pick was this one here. You guys at home doing okay? Anybody lose anybody on any of these steps? Should be able to do the rest of the lab then from Now that you have all the graphs, I'll let you finish your analysis up. I'm going to stop the recording of class here.